Let's conclude the equatorial Rossby wave part of these eigensolutions by looking at the structures and the induced velocities, the perturbation velocities that we introduced in the linearization, which are essentially these for different meridional modes. So UN, Vn, and the vertical mode written in terms of the geopotential, which in the ocean will be the sea level height, and the atmosphere will be the geopotential height. Okay. So those are specific examples, specific modes, and let's see. The dispersion relation we wrote in terms of the meridional mode, basic state, beta, and zonal wave number, with this term defined to simplify this expression. I'm just revising these. Using those, we can write the zonal velocity and the meridional velocity, essentially u prime v prime, but now you are basically thinking of u and v associated with the waves, and then we will also add the basic state to it. As we said before, the odd Hermite polynomials are asymmetric, and the even ones are symmetric. So we are looking at different depths, 50 and 100 meters, different modes, so n equal 1 and n equal 2, and we are looking at zonal velocity and meridional velocity. So you can see that the background state here clearly broadens the structure in the westerly basic state. So that's the equatorial trapping we are talking about. As the depth decreases or the basic state becomes easterly, the equatorial trapping is more confined, whereas if you increase the depth or if you make the basic state westerly, the trapping latitude increases. So you can see there is small difference there. The depth effect dominates. Obviously, you can see the difference between the blue, black, and the red line is larger here than here, because the impact of the depth is larger in terms of expanding this latitude of equatorial trapping. Similarly, for n equal 2, you can see the difference is much larger here in terms of the impact on equatorial trapping for the symmetric mode, and broadened, but the difference between the westerly state and easterly or basic state is somewhat reduced because you have the depth impact being much larger. But you can clearly see a great shift in the equatorial trapping latitudes here. This is somewhere around 25, between 20, let's say 20 degrees, and here it's almost close to 30 degrees. Similarly, meridional velocities, you can see they're much smaller as well. The scale is from 10 to 10, whereas this is from 4 to -2. So meridional velocities obviously are much smaller than the zonal velocities. Okay, just in the balance itself, there are impacts of the zonal versus meridional impacts of the beta, in the sense that it's harder to move meridionally because the Coriolis changes. Beta becomes a stronger restoring force, whereas in the zonal, the the constraint is much less. Intuitively, you can also see that the zonal winds tend to be much stronger than meridional winds in general, right? Same for currents in the ocean. Okay, so the same story here, 50 meters for N1 and N2. You can see the massive difference between the first mode and the second mode for the same equivalent depth, and large differences for the changing basic state. Whereas when you increase the depth, those differences shrink. But the main message there is that the equatorial trapping is also greatly affected by the depth. Okay, this is the eigensolution for the equatorial Rossby waves for zonal velocity component, meridional velocity component on the geopotential. So you can see the n equal 1 and 2 mode Now instead of the velocities, we are looking at the perturbation to the geopotential in the atmosphere or the ocean. We haven't made it specific yet. So for 50 meters, the perturbations are smaller for the first meridional mode and much larger for the westerly mode. So the symmetric solution here, the westerly basic state is greatly affecting the geopotential, right? Of course, much larger equatorial trapping latitudes, and for a greater depth, that difference is still there, but much small, well, somewhat smaller. But again, the equatorial trapping latitudes are greatly increased for the westerly mode compared to the easterly mode. Obviously, background non-zero background state is in the middle of the easterly and westerly state, so you can see those impacts. So just get intuitively comfortable with these. The impact of choice of the depth on the eigen solutions for the equatorial Rossby waves for wave number 5. So Ka is set to 5. This is the first meridional mode. Okay, this says n equal 2 here, which is wrong. This is actually n equal 1. And for 400 meters and 50 meters, once again showing the greatly reduced equatorial trapping latitude when you have a shallow water as opposed to a deeper water column or air column. So as the fluid depth increases, the latitudinal extent of the wave increases, and you can see the typical asymmetric Rossby wave structure. You may think this is symmetric, but remember that when you go south, the direction of the sign of Y changes. So this is not symmetric. This is actually anti-symmetric. But you can see the wave having the eastward and cyclonic flow here, and westward and anticyclonic flow here. So the sign switches, of course. So this is counterclockwise is cyclonic in the southern hemisphere, and this is anticyclonic in the southern hemisphere. So those are solutions plotted, hopefully make much more intuitive sense. Okay, so let's leave this here and come to the next podcast. I'm keeping these short so that you get each point. We are still doing equatorial Rossby waves, but we are looking at the impact of the mode number, so n equals 0, 1, 2, depth number 50 to 1000 or whatever, and the impact of basic state in terms of easterly, westerly, and resting state. Okay, get good sense about these things.